So with the conclusion of the root test, we've learned all the different types of convergence tests that we're going to learn in the class. What we really need now is a strategy for choosing an appropriate test given some particular series that we're given to work with. Because in the homework, it's very much, you're given a test and you're supposed to apply it to 3 or 4 different, practice problems. But you already know which test to use. Often on like a review sheet or an exam, that's not the case. You have to actually decide first which test to use and then apply the test. So let's look at some identifying features of different series so that we can pick an appropriate test to work with. So first off, does the series have an alternating term? All right, that's generally pretty straightforward to identify. Like for instance, if it's got something like -1 to the n in it. If it does, chances are you're going to need to use the alternating series test and possibly determine if the series has absolute or conditional convergence. It is possible that the ratio or root tests might apply, but regardless, make sure you include the test used and then the supporting details as to why your result for convergence or divergence, is supported. All right, so that's generally a very easy thing to see right off the bat. Then next, look to see if it's some familiar series, like a p-series or geometric. Now, generally, that's not going to be the case. You're not going to just get a problem that is just a p-series or just a geometric series. Generally, we use those within other tests, like a direct comparison or a limit comparison, for instance. But if it is, then, provide details why the series converges or diverges, state the result. Fairly straightforward. All right. If it's very similar to a p-series or a geometric series, then that's when you might want to use a comparison test. The direct comparison is a great one to use from the beginning, or the limit comparison, but I generally reserve the limit comparison for polynomial functions. All right, then if that doesn't apply, compare the functions and the numerator and denominator, and see if the numerator and denominator are in different function classes, and possibly if one is a factorial or an exponent. All right, so if they're in different function classes, the ratio test is a great possibility. The root test, you would probably need somewhere some power of n. But if you see numerator and denominator in different function classes, usually the ratio test is a great choice to use. But if the numerator and denominator are in the same function class, well then the ratio test generally doesn't give a result in that situation. All right, and the limit comparison test is actually very good in that situation. But this might overlap with some that you might originally have seen that the direct comparison test was worthwhile to use. So it's not always a clear indicator which test to use exactly. This is just some guidelines here. But if they're in the same function class, usually the limit comparison test works pretty well, especially for polynomials. And that would be the numerator and denominator both being polynomials, so let me say rationals. Okay. And then, if none of those really apply, the one thing that you should always be thinking of is just, are the terms of the sequence going to 0? So, and then this isn't like a specific order of how you should be thinking about these either. If you look at the sequence, then you can kind of tell right away that the terms of the sequence just aren't going to zero, then it might not need any of these other tests. You might be able to just do a quick limit and prove using the divergence test. So never forget that that's always a possibility. And then the last one that I use, simply because it is a bear often to work with because you have to perform an integral, but if all else fails, if it looks like an integrable function, you can always try the integral test. Okay, so just kind of keep that in mind. These certainly aren't rules here. These are just kind of guidelines and coming up with a thought process as to how exactly to determine. And I've got a few examples that we can practice with this thought process, so let's work through those. So we want to determine which convergence test is the best to use, and then find out if the series converges or diverges. In addition, if it happens to be an alternating series, we want to know if it's conditional or absolute convergence. All right, so this particular function is polynomial. All right, so rational. I should be careful in saying that. So rational function, I always think that the best choice there is the limit comparison test for that. So I'm going to do the limit comparison test, and I'll compare to series n equals 1 to infinity. If I take the degrees and reduce, I would have 1 over n. So that's what I'll compare to, which is the harmonic series, so it diverges. Okay, so the test itself, I need to do a limit as n goes to infinity, and I'll take the original series and technically I'm dividing by the new series, the known one, but I'm actually just going to multiply by the inverse, which is the same thing. So that right there would give me a limit. This would be n cubed plus 2n squared over n cubed plus 3n squared plus 1. The leading terms here are both n cubed, and because of that, the ratio of leading term coefficients is just going to be 1. Now, it's easy to get these all these tests mixed up. But the thing is, it's the ratio test where the test fails if the ratio, that limit is 1. The limit comparison test, we just need the result to be non-zero or finite. So that's not equal to 0 or infinity. So therefore, it will do the same thing as the known series, so that tells me this diverges by the limit comparison test. Okay, let's take a look at another one. Same instructions, we just want to see if this series converges or diverges, and if it's alternating, we want to know conditional versus absolute. Now, there is an alternating term because we have -1 to the n plus 1. So you might be thinking that the alternating series test would be the best to use. And that probably would work fine, I'm not sure. But there is also the ratio and the root test that can test for absolute convergence. And I think absolute convergence would work here because if you'll notice, the numerator is linear, so that's a polynomial class. The denominator is factorial, so that's going to go to 0 a lot faster. My intuition is that this is going to converge very easily using the ratio test, and the ratio test should be especially easy to work with algebraically because of this factorial. So that's what I'm going to use. So ratio test. And what we do is we take a limit as n goes to infinity, the absolute value of the n plus 1th term. Now, I could put in here -1 to the n plus 1 plus 1th term, I guess would be n plus 2. But the thing is, the absolute value around this is not necessary, because the -1 multiplier is only either going to make this term positive or negative. But the absolute value is going to make every term positive, so I don't actually need to include the -1 to the n plus 1 term. So I'm going to make this 3 times n plus 1 over n plus 1 factorial times the inverse of that, which would be n factorial over 3n plus 1. Then we have the limit as n goes to infinity. In the numerator, that would be 3n plus 3 plus another 1, so 3n plus 4 over, I'll take out the top item off of that factorial, and the factorials will cancel then, so the remaining factorials will cancel. Next, I have the limit as n goes to infinity. In the numerator, it's still 3n plus 4. In the denominator, I can actually multiply these two. So that would be 3n squared. All right, so then plus 3n plus another n, so plus 4n plus 1. But really, the last terms there don't really make a whole lot of difference. It's just that the leading terms, the degree in the denominator is larger. That's going to take this limit to 0. And with the ratio test, that proves convergence. So this converges, and in fact it converges absolutely by the ratio test. Okay, here's another one. Now, looking at this series, just kind of first examining like how quickly these terms are going to infinity. E to the n is exponential, n cubed is polynomial. So the exponential function is going to go into infinity a whole lot faster than the polynomial. So if the numerator is growing that much faster than the denominator, these terms should be just going to infinity altogether, which means that I might be able to just use the divergence test. So let's try it. So the divergence test, I look at the limit as n goes to infinity of e to the n over n cubed. And to evaluate this, I would need to use L'Hopital's rule. L'Hopital's rule tells me that the derivative for the numerator e to the n is just itself. The derivative of the denominator would be 3n squared. Now, I'm not really much closer. I would have to do another round of L'Hopital's rule. So limit n goes to infinity, e to the n over 6n, and still infinity over infinity type, so let's do one more round, e to the n over 6. Now we get a result with L'Hopital's, with the limit itself. The numerator is going to infinity, but the denominator is no longer changing. So this is going to infinity, so this diverges by the divergence test. Remember, you cannot prove convergence with the divergence test, but you can definitely prove if it diverges. All right, one more here, and I have, looking at this series, 3 to the n over n plus 1 to the n, I've got these powers of n, and that's generally a good indicator to use the root test. So I think that's what I'll do. So I'll use the root test here. Using the root test, I would be taking the limit as n goes to infinity of the nth root of the absolute value. I'm going to go ahead and factor out this nth power from the numerator and denominator. So just like that, and that should still be an absolute value. The nth root and the nth power cancel each other out, leaving me with absolute value of 3 over n plus 1. And the denominator is changing. Numerator is constant, so the value of this would go to 0. And when the value of this limit goes to 0, that tells me that this series converges by the root test. So those are the types of ways that, or the types of thinking that I go through when I'm trying to come up with a series to apply. And especially if you use the function classes by velocity as a guide, you can generally tell if it's supposed to converge or diverge right off the bat. And knowing if they're in different classes or if they're in the same class, that is a good indicator of what type of test to use, whether it be like a ratio test or a comparison test. So that would give you some good guidelines to work through these, and hopefully they go well for you.